Hongseok Yang, who's at KAIST in South Korea, and as probably most or all of you will know, these days he works on probabilistic programming and on machine learning PL interface things. Hongseok, take it away.
Yeah, thank you very much. Thank you. Screen. Yeah, so thank you all for, also thank you for inviting me to this workshop, excellent workshop. And I mean, in Korea, I have been speaking everything in Korean for quite a while. So my English may get stuck at some point. So I hope you to understand. And let me just prepare a little bit before starting. So enable chat box. Okay. So what I'm going to talk about today is the work that my colleague presented in PAPO 2020. But I want to say a bit, I mean, I thought the work had something interesting, especially not exactly the solution that we propose. I thought more interesting bit is about the problem that we try to describe. So the purpose of this talk is to explain to you about certain kind of software verification problems that can arise in machine learning.
Hongseok, forgive me. I realize
Yes.
I am remiss in one of my duties. I should have reminded people that this is being recorded. So if they don't want to be recorded, they should ask questions by the chat. Sorry for that.
I mean, it's fine. Okay, thank you. So, I mean, the machine learning softwares you can see almost everywhere nowadays. And in fact, quite a few people in verification and programming language community has looked at some issues in machine learning. And especially people working on verification and model checking, they look at the bugs or software errors in machine learning or some software, I mean, that uses machine learning engines. And there are a few types of errors that people looked at, but the majority of the people look at bugs in the trained or learned model. Okay, so for instance, suppose we trained a model that can distinguish dogs and cats in an image, but then the kind of thing we don't want is that if you insert a noise into the image very little bit, if the classification changes dramatically. So for human eyes, it's still dog, but certain pixels in the image is changed a little bit. And sometimes that kind of a very small noise can make a huge difference in the learned or trained model. So people call it robustness property. And Marta, as well as Martin, who are going to give a talks, I mean, later they did excellent work on this topic. Also, some other people also from the machine learning community, as well as PL community, they looked at fairness issues in the learned or trained models. So suppose we are using some machine learning engines in a software that, they make a big decisions in a court, okay? And with that, we want that software to be fair. That software doesn't have any bias against race or sex or age and so on. And people are working on how to guarantee or how to check this absence of bias in such a software. Okay. So these are all mostly about can we prove some properties or guarantee something about trained or learned models. But there are other kinds of errors in machine learning software which are not studied that often. They are the errors that happens during the training and inference algorithms. Okay, and yeah, these inference and the training algorithms, they are approximate, so they are only solve some optimization problem approximately. But as I will explain later in this talk, these algorithms sometimes have terms and conditions which are not explained very explicitly when these algorithms are presented to students or users. So if these algorithms are given some bad inputs, which are typically programs or models, and then these algorithms perform very badly. And then you have no idea whether that bad performance is due to bugs in your inputs, which is your model programs, or maybe because of the approximation that's caused by these algorithms. So this is more like about the developers of or users of these machine learning techniques instead of the real end clients of some artifact produced by machine learning algorithms. But I believe these problems can also be addressed by using some PL techniques and have some interesting, we have something to contribute to this part of the area, this kind of problems. So let me show you some examples from some of my work done with on the machine learning algorithms with my colleagues. So I don't think you will understand this algorithm at all, but this is just some curve that shows, the so-called the result of posterior inference of running an algorithm. You don't understand anything except that x-axis say it's an iteration of the algorithm. So as the iteration goes, we expect the outcomes of the algorithm will improve. So the curve is expected to improve. And in fact, you can see that the blue curve and red curve improves in this picture. But I want to point out this blue one. Blue one is done by so-called stochastic variational inference with so-called reparameterization trick. That is, in a sense, de facto algorithm that people use quite often. But you can see that the red one is the one that we proposed in that paper. But you can see that the blue one, which is supposed to perform well, it actually gives a suboptimal performance. That is because this algorithm has some requirement, which is that the inputs to the algorithm, which is a program that has to satisfy some differentiability requirements. And here we are giving input which doesn't satisfy that requirement. So it's not differentiable. Still, the algorithm doesn't crash, but it just shows it as a suboptimal performance. And distinguishing this type of errors in an input by testing or just looking at the outcome of the algorithm is extremely difficult because we don't really know whether this is the outcome that we should get by running this algorithm or this is the caused by some problems in the input. So the point, the key message of my talk has two key messages. So the first key message is that often the machine learning algorithm have non-trivial assumptions. I'm going to talk about specific machine learning algorithm called stochastic variational inference, or sometimes called black box variational inference algorithm. These algorithms have non-trivial assumptions. So if you happen to be a user of these algorithms, be careful. Maybe you are giving inputs to these algorithms which violate these assumptions. Violating this assumption doesn't lead to the crash. It just gives you some kind of poor outcome, poor achievement by these algorithms. Okay, so that's one message of my talk. And the other message is that now checking the inputs, which are typically programs, satisfy these requirements can be a good opportunity for programming language and software engineering and verification researchers. I'm going to give you examples of these problems in the context of probabilistic programming and the stochastic variational inference. But I believe that in different kind of parts of the machine learning, also checking the satisfaction of these requirements can be a good research opportunity. Okay, so remaining maybe 15 minutes, I'm going to tell you about particular things, which is stochastic variational inference in the context of probabilistic programming. And I will tell you about what are those requirements and what are the potential issues that can happen because of these requirements. Okay, so I'm going to use the probabilistic programming, which especially I'm going to use the specific probabilistic programming language called Pyro, which supports Bayesian inference together as well as deep learning. So this language is sometimes called deep probabilistic programming language. And this language is on top of Python. And the purpose of the program in this language is to describe a probabilistic model. So the examples program that you see is designed to describe probabilistic model on for model with two random variables. One random variable is called V, the other random variable is called O. And one interesting bit about this model is that instead, we are not just specifying probability distribution for V and O, but we also specify specific values of one of the random variable O. So we're going to describe probability distribution for V and O, and then we said by the way, we observe the value of one of the variable, which is the value of the variable O. The observed value is equal to 0. And what we are looking for is a conditional distribution on the variable V. So intuitively, V is a hidden cause, V is observed data, and we are describing a model that describes how these hidden cause and observed data are related probabilistically. And at the same time, we're providing information, specific information about observation O by saying the value O has a value 0. Variable O has a value 0. And then we want to combine all these things together and come up with a new distribution on V that brings our understanding or a description of the model as well as the information coming from the data. So that's described by the conditional probability distribution. Okay. And from the program, it's quite simple. It's a randomized program. So we first describe V is a sample from normal distribution, mean 0, standard deviation 5. So this normal, I mean, if you're not familiar with this, don't worry. It's just that the value of the V is very close to 0, and its range is between -10 and +10, 2 times standard deviation plus minus. And then for the second random variable O, and as I said, we define second random variable. At the same time, we specify its value. It's a bit like we are specifying a bit of post condition. And then the distribution used for the second variable, depending on the value of variable V. So if a variable V is positive, the distribution for O is normal 1, 1. If a variable V is not positive, distribution for O is normal -2, 1. Again, you don't need to understand the normal distribution very much here. The only thing you need to understand is that observed value 0 is close to the mean 1 in the true branch, then mean -2. I mean, distance between 1 and 0 is 1, -2 and 0 is 2. So observation is, in a sense, support. The true branch is more likely to happen. So true branch is more consistent with the observation than the false branch. Okay. So we are expecting if you compute the conditional distribution on V, then the probability mass for V being positive is larger than probability mass for V being negative, because positive, the true branch, which is happening when V is positive, is more consistent with observation. So in fact, this is a pictorial description about probability distribution on V. So before the observation, this blue curve describes probability distribution on V without observation at all, okay? So without conditioning. So then you can see it's a symmetric, it's centered at 0, and it's a fully symmetric. But the red or orange curve describe a conditional probability of V under the condition of O have a value 0. Okay. Then as I said, this O have a value 0 is more consistent with V being positive. So the probability of V being positive went up, probability of V being negative went down. Okay, so that's and then the purpose of writing this model is to compute this orange distribution. And then probabilistic programming language have a built-in machine learning model that computes such a approximation of such conditional probability, which is also called posterior distribution. And I'm going to talk about the specific inference algorithm called stochastic variational inference. The idea of stochastic variation inference in the context of Pyro is that we ask the user of the algorithm to write a template. It's something like a template-based verification technique. We write a template, which is a program with parameter theta, and that template is written Q in the slide, and that describes a probability on variable V that we care about. But you can see that the first instruction in the Q is a parameter declaration. So it's initialized to 0, but its value, the value of parameter theta, will be changed by the variational inference algorithms implemented in Pyro. And then second instruction said that now the distribution is a normal distribution centered at theta. And then the idea is to find appropriate value of theta that approximate this orange distribution, this conditional distribution or posterior distribution. Okay. Then appropriate value of theta is going to be the one that you see on the screen. And I mean, so the value theta has to be positive because conditional distribution, probability of V being positive is larger than probability of V being negative. So the theta value, appropriate value of theta have to be shifted to the positive side. And what we want is that the one by the machine learning algorithm is that machine learning algorithm computes appropriate value of theta so that I can describe this orange distribution well. Okay, I hope
So, we've got about 5 more minutes, depending how much question time you want.
So I think I maybe spend like 5 minutes for the question Q&A. So maybe 10 minutes I have, perhaps 7 minutes.
Yeah.
Okay.
Okay.
Okay. So now how does this optimization work? So typical optimization is done by minimizing so-called KA divergence. So KA divergence is you can roughly speaking think of it as a distance between two probability distribution. So minimizing KA divergence is the objective of this optimization. And then the machine learning algorithm solve a stochastic variational inference algorithm solve this optimization objective. And then KL is defined by the probability ratio. So you can see it's an expectation of log probability ratio. And this value is equal to 0 if two probability distributions are the same. It has a positive value when they are different. And then the algorithm optimizes this by gradient descent. So we want to minimize this KL. So we compute the gradients of this KL with respect to parameter theta. And then we iteratively update theta by following the downward directions, which is minus gradients. But in practice, this gradient is not computable. Well, I mean, you can't really compute it. It doesn't have analytic form. So we use an approximate algorithm, which is some kind of estimate, the randomized algorithm that produces an estimate of this KL. So that's how this algorithm works. So, okay. Now, what can go wrong in this context? There are 3 things that can go wrong. The first thing is that KL may be undefined. Okay. So I said the KL is defined by the average probability ratio. But one problem is that this ratio is division. So we may have a divide by 0 error. So denominator, which is a P of V conditional distribution, may have a 0 probability. But numerator, the approximate probability distribution, may assign non-zero probability. So we may have a divide by 0 error. But then another perhaps unusual problem is that this expectation may be undefined. This expectation is integral. Integral is not always defined. Sometimes it's infinite, or so in this case, sometimes it's infinite. So it's not always defined. So that's a potential second problem. The third problem is issue 2 is that we are thinking about the gradients, but this KL may be non-differentiable. So when you compute the gradients, this very idea of the gradient may be undefined. The third is that typically this estimator has some guarantee, especially it has so-called unbiased guarantee. That's very important to ensure the convergence of this type of algorithm. But this guarantee has terms and conditions which are not explained very often. And these terms and conditions may be violated, which means that this estimator for gradient of KL may produce something not quite good. Okay, so these are the 3 problems that I just mentioned: undefined KL, non-differentiable KL, and the wrong estimate of this gradient of KL. Then let's look at these 3 problems a little bit more. So for undefined KL, as I said, KL is defined by the average log probability ratio. So there's an integral, and then the log inside the log, there is a ratio. And then there are 2 potential problems. One is this ratio may have a divide by 0 error. So, and then the second problem is the integral may be undefined. And then you may ask, can this really happen? And it actually happens. So this is the example program from the Pyro webpage. They may have changed, now, but when we do our work, this is the example from Pyro webpage, which is about some Bayesian regression example. And then in this case, KL is undefined. That is because, it has a bad integrand problem. So the sigma is one of the variable. I mean, one way to see this is that the sigma has a uniform distribution 0, 10 in P, and it's a normal distributions in approximate distribution Q. So one thing you can see is that sigma cannot have a value, say, minus 0.1 or minus 0.2 and so on in P. On the other hand, the Q sigma can have a negative values. That leads to the divide by zero error. Okay, so this have a divide by zero error. Then you might think, oh, maybe it can be fixed very easily by just using exactly the same distribution in P and Q. So in the Q, we just use exactly the same normal, the uniform distribution. So this simple divide by zero error doesn't happen. But this also, then if you do so, then we have an integrability problem. I mean, I don't want to go into the detail, but if you do this and compute the KL, essentially the KL involves this integral of the sigma, which corresponds to this sigma random variable. And then the integrand is some constant square divided by sigma square. You know that the value of sigma becomes close to 0. Sigma 1 over sigma square is infinite. So the integral is not defined. Okay. So fixing this is not obvious. I mean, if you do the other way around, using just normal, again, we have a problem. This case, we have a integrability problem. So it requires some care to fix this properly. Okay. Now, the second problem I talked about is a non-differentiable KL. And this problem also can happen. So this is the model that I showed you in the beginning. Now, let's think about guide, where we have a parameter theta, but for approximating distribution for V, we use a uniform distribution between the theta minus 1 and theta plus 1. So and once you do so, KL is well defined in this case, but KL is non-differentiable. So this is the graph of KL. Then you can see that there are two angles in the KL, and actually they are the non-differentiable point. And this non-differentiability actually comes from the if-then-else branch in my program. So if theta is smaller than minus 1, it only look at the true branch between minus 1 and 1. You look at both true and false branch. If it's plus 1, you only look at the true branch. So I will spend a bit 2 more minutes and then finish. Okay. I started 2 minutes late. So the third issue is a wrong estimate. And then I said typically this estimator of the gradient of KL is a randomized algorithm. And it often comes with a so-called unbiased guarantee, which means that on average, because it's a randomized algorithm, we can talk about on average, it computes the right value. In other words, in expectation, it computes the right value. And the most well-known algorithm that people use is so-called score estimator. You don't need to understand anything about this. It works like a sample V0 from approximating distribution and compute the quantity that you see on the screen, gradient of log probability times something. And it comes with a guarantee, which say that the on average is equal to the gradients. But this guarantee comes with the terms and conditions. Okay, where these terms and conditions come from. And if you look at the proof, then in the proof of this equality, actually, here's the one important step in the proof. The steps say we want to switch the gradient, which is a differentiation and integral coming from the KL. And this switching, differentiation, and integration is not always valid. There are certain things that has to be met to ensure that we can interchange gradients and differentiation and integration. And this problem can actually also happen in practice. This is the same example that I showed you before. Now, for this program, if you look at the value of KL when theta has a value 4, this gradient is not equal to 0. But if you compute the score estimator in this case, then you will sample V0 from the distribution Q theta and compute some gradient of a log probability times something. But because the uniform distribution is always 0.5, probability of Q is always 0.5, so it's equal to 0. So it's always 0, and that's on average is not equal to some positive value that we should have here. So this problem actually can happen, and checking this, ensuring that this problem doesn't happen is quite tricky. Okay, so actually I'm done my talks. I mean, my talk was mostly about explaining these problems. So how to check these properties do not happen. I mean, these problems do not happen. And then just out of time, I suggest you, if you're interested, you can look at our pop-up paper. It doesn't have a complete solution, but it has some techniques that ensure how these problems do not happen. And then just the final remark is that this type of ensuring training, the input to the training actually meet the requirement is not explored that much. So I think it will, perhaps if you look at this problem from the verification hat, there will be more opportunities. Okay, so thank you very much.
Okay, thank you very much. So we have time for maybe one or two pretty quick questions. If you want to ask them in the chat or stick up your hand and I'll call on you. Maybe I'll ask one. So I don't know if there is sort of a sensible corpus of example code that you can look at, but do you have some feeling for just how often these problems come up?
So for my experience, these type of problems, the problem actually I'm talking about are problems on the training side of the machine learning. And this problem happens, I have so the examples you can look at in the Pyro web page, there are, the extension of this work, we're working on some checking differentiability or some other various continuity properties of these models. And one case I also have a few, so some examples have these type of problems as well. And then also my personal experience is that I and my colleagues working on some reinforcement learning algorithms, and the students with the implementation told us that, oh, that algorithm doesn't work. But it turns out what really happened is that they made a mistake in tensor reshaping. So they just reshape in the wrong way. The type is correct, but it's reshaped in the wrong way. And it gives a suboptimal performance. We thought there was a problem in the algorithm, but it turns out actually there's a problem in the code.
Okay. Do we have any other questions? No, then thank you again.
Okay, thank you very much.
So do we have Marta?
Yes.
Okay, so do you want to share your screen?
Yeah, I can try.
So next speaker is Marta Kwiatkowska, indeed at the University of Oxford for quite some time, not at the University of Birmingham. We'll be talking about probabilistic model checking for the data-rich world. So,
okay, thank you, Peter. Thank you for the introduction. I think what this is showing is that I had not managed to register, so it's using the old data in the database from last time that I was a participant at the Newton Institute, which was a great event at the time. So thank you for this invitation. I'm going to tell you about my work that has actually taken sort of, about 20 years of my time. It's about probabilistic model checking. I don't have much time, so I will just say what you can do with it, what we are focusing on right now, and where we are moving towards. And in particular, this is to address the world dominated by AI and deep learning. So I'll start with the motivation. The motivation is that software is everywhere. I think right now software is helping me to talk to you. It's in our mobile phones, but it's also in autonomous cars. And the world is stochastic. There is a lot of component failure, environmental uncertainty, communication delays. But at the same time, we users, like me and you, now we expect Zoom to work. we expect software to work. So we expect predictability and high integrity. And there are a whole range of properties that are associated with software working correctly: safety, reliability, robustness, security, and they are all expressible probabilistically. For example, we want the probability of an airbag failing to deploy to be very low. So this talk is about probabilistic model checking, and probabilistic model checking is automated or automatic verification for probabilistic models. Now, the models that we are working with tend to be variants of Markov chains or Markov decision processes. Typically, they would have discrete probability distributions, but they may also have decisions within them. So the idea is to do proofs of correctness, but proofs of correctness algorithmically, rather than using a theorem prover that's perhaps driven by a user. And specifications are given in temporal logic, in some appropriate probabilistic variants of temporal logic. So examples of these quantitative probabilistic properties for which you can actually obtain a guarantee are here: reliability, okay, the probability that my smartphone crashes is very small. There are quantitative extensions, so you can also annotate the models with numbers such as energy usage, and you can verify properties about them. And in terms of the specifications, they are expressed in temporal logic, either CTL or LTL, with the probabilistic quantifier. And this example here, which was actually verified using a probabilistic model checker, is that whenever the airbag is triggered, then the probability that it will deploy within 20 milliseconds is at least 3 nines, 0.999. So probabilistic model checking is embodied in a tool, probabilistic model checker Prism, that was developed in my group with Dave Parker and Gettin Norman. We started working on this in 1998. So even though the first algorithms already existed in the 1980s, early 90s, the Prism was enabled by a paper developed in 97, which proposed the first symbolic meaning BDD, a BDD extension of the probabilistic model checking algorithm. Now, Prism was first released nearly 20 years ago in 2001, but it's gone on, it continued throughout with various releases, and it has several offshoots. One of these is Prism Games, that I'll say something a little bit later. It is now widely used, and it is used not just internally by my group, but also externally and independently. And it has found genuine flaws in various real-world systems. So what is Prism built on? What are the enabling technologies behind Prism? The primary enabling technology is symbolic, and this started off with binary decision diagrams, and in fact multi-terminal binary decision diagrams, which is an extension that allowed us to represent probability matrices and develop the very first algorithms. But more recently, we are also incorporating SAT and SMT and various other solvers in the algorithms. In addition, the probabilistic models that Prism can handle are also probabilistic extensions of timed automata. So that draws on all the technology that was developed in that context, including digital clocks, zone-based algorithms, polyhedra, etc. Now, the main algorithms for probabilistic model checking actually compute numerical answers, so numerical values for the probabilities, but we also allow statistical model checking. This is a sampling based, so your samples are runs, execution runs, and then the statistical method uses statistical hypothesis testing to estimate the probability value. And in addition, there are compositional methods because there is always the need for scalability and many, many more techniques. Beyond symbolic technologies, what PRISM has more recently focused on, this is for models that include decisions, for example, Markov decision process models or games that I'll mention later. For those models, it is also possible, more or less using the same algorithms that are employed to do verification for temporal logic, it is also possible to actually synthesize a controller or strategy or policy. These are all synonyms in that context, that is corrected by construction. So for a given model and a given property, it is also possible to compute an optimal controller. And obviously this has many applications in the context of robotics, security. I'm giving you an example of an attack defense tree. Now, more recently, we have also extended probabilistic model checking to handle games. Now, why games? Okay, we know that in games, we have players, independent players, that they compete or collaborate, and they may have conflicting goals, and they make autonomous decisions. And of course, this is the main reason why games are appropriate models to represent current situations, including from autonomous driving, but also from robotics, where you have independent agents and they may have, conflicting goals. And what we need is we need to learn from researchers in economics for how to employ game theoretic techniques for negotiation, strategic game playing, and perhaps incentivizing the correct behaviors. And this is already being employed in the context of autonomous driving for situations such as merging or roundabout, crossing roundabouts. And further on, one other enabling technology is the fact that even though in order to do model checking, you have a model and you provide a specification, well, a lot of the time, the situation that you would have is that you would have several specifications and they may conflict. So optimizing for one particular specification is just not good enough. What you may need to do is to optimize the trade-off, because in optimizing for one, that means you are decreasing the optimality of the other. So PRISM can also handle multi-objective properties, and it can produce quantitative results in the form of the Pareto curve, where each point on the Pareto curve would then correspond to a point that's optimal, in a sense that it's an optimal trade-off between two values. So this again draws on techniques from engineering and optimization, in particular multi-criteria optimization. Now, what is PRISM useful for? Well, the very first example that we did, that's a very complex real-world example, was the Bluetooth device discovery protocol. And for that, what we did is we computed the worst case expected time to deliver a message. And this is something that distinguishes model checking verification techniques from simulation-based techniques. Because in that model, this was an absolutely huge model, and with simulation, it was just not possible to obtain that worst case response time. PRISM has also been used to find flaws, known as counterexamples, so execution traces to error in various communication protocols, including anonymity protocols. Many of the communication protocols that you know about use randomization. You may not be aware of that they use randomization. So probabilistic model checking made sense. A number of examples that PRISM has been used for came from biology, where it was used to develop a model to actually prove or disprove a particular hypothesis. To develop a model, populate the model with some real-world data, and then prove or disprove a hypothesis. PRISM can also be used to evaluate and optimize designs, and in particular, the multi-objective analysis was used to analyze designs for robotic applications where you might be concerned about the trade-offs between energy usage and efficiency. PRISM can also be used to build models that are from data-driven. So, for example, user activity patterns. You can develop HMM, hidden Markov model, like models, which then can be queried. And of course, I've already mentioned the planning and robotics applications construction of an optimal policy. So if you are interested, PRISM has a website. It's currently on release 4.7, and PRISM Games is a separate tool. There are numerous case studies. I've already referred to some of them. The ones that I didn't mention were DNA computing, ADAS assistance. So this is a driver assistance system. Just think of Tesla Autopilot, smart grid energy. And there are also a number of case studies that were developed independently of the PRISM group that I mentioned here, including programmable networks, transistors, cell decision-making, and then I've already mentioned user activity patterns. So PRISM, over time, say over the past 20 years, has developed into a technology that's pretty mature. It's being incorporated within workflows as a backend, so you can translate your favorite model into the PRISM modeling language and incorporate it, so you can generate the model, generate the specification, and incorporated it within the workflow. I don't have time to talk about them, so I'll just say something about what we are focusing on right now. We are focusing on stochastic game models. Why? Because stochastic game models embody the autonomous nature of agents that we want to model right now. And there are many, many applications, robotics, autonomous driving, but also virtual agents, assistants, robotic assistants, etc.
Marta, can I just interject to encourage the audience to start adding questions to the chat and to warn you that this is sort of a 5-minute tick?
Okay, thank you.
Okay, thanks.
Thank you. Yes, so PRISM now has an extension called PRISM Games, which started off with turn-based games. And it had an extension of the logic based on the probabilistic CTL extension, and also drawing on concepts from ATL, alternating temporal logic. It's coalitional variant, but it now supports concurrent stochastic games. Now, in concurrent stochastic games, we can model situations where agents have distinct objectives and they are no longer zero-sum goals. We also allow Nash equilibria. So for those of you who know about the technical details, they are more precisely subgame perfect epsilon Nash equilibria rather than pure Nash equilibria. And in addition to that, we also support social welfare. We support the selection of optimal social welfare or social cost Nash equilibria. These minimize or maximize the sum of expected rewards. Now there is an implementation in Prism games, which is at the moment non-symbolic. Well, it has some symbolic features in SMT in algorithms, but the models themselves are not represented symbolically. And there are already a number of examples, including the Aloha communication protocol, which is based on games. So what does model checking for equilibria involves? Now, because we are talking about iterated games, we support both finite horizon and infinite horizon properties. What actually happens is if you unfold, starting from the initial state, you unfold the game into a tree, and in fact you need to compute, you have to construct a normal form game and compute a Nash equilibrium in each state. Now for finite horizon, the values are computed using backward induction. This is a standard method that's known from game theory. But for infinite horizon, we have to use value iteration to approximate the values, the utility values as the limit. And this is also improved by employing model checking and model checking for two coalitional variants from the point where one of the agents has reached its goal. The implementation makes use of SMT solvers, and for the M coalitional variant also of nonlinear optimization solvers, and supports strategy synthesis. So I mean equilibria strategy synthesis. Just a very quick example is a secret sharing example, which goes back to Halpern, and it was analyzed, its correctness was proved, but the analysis was theoretical, and in particular there was a hypothesis there which we verified on this model. Now this is a protocol that aims to induce cooperation by using uncertainty. So in particular, you have a number of autonomous agents. They each have an unfair coin with the same bias. And they start in step one by flipping the coin. Now, if the coin lands on heads, then the agent is supposed to send its share of the secret to the others. And in step two, everyone reveals the value of the coin to the other agents. And the protocol will end when all agents obtain all shares and therefore can reconstruct the secret. But what this protocol allows them to do is to cheat. Okay, and to cheat means that they will just refuse to send the share of the secret to the other agents. And in this paper, there was actually a specific variant of the protocol which considered rational agents. So rational agents would maximize their utility, but these rational agents are also allowed to cheat. So the cheat option is one of the actions that they can choose. An altruistic agent just simply follows the protocol, just behaves absolutely correctly, and the Byzantine agent can fail. So just probabilistically fails and can refuse to send the share of the secrets. So we have analyzed different settings for this protocol. So what you see is, you see at the bottom here the bias. Alpha is the different values of the bias and the expected utilities. So there was a theoretical analysis which said that the rational player would cheat given a high enough probability. And indeed, you can see it here from probability 0.5, the rational agent cheats, just its utilities increase. So this is one example, and this example actually could not be solved in a true coalitional variant. Okay, so what are we doing next? So PRISM models up until now were described using a language that's essentially Dijkstra's guarded command language with probabilities, but it does not support model learning. But we know for AI, for robotics, for the various types of applications that I've used in my motivating slides, this is very important. So what I need to be able to do is not just to model this Markov chain or Markov decision process, but I also want to be able to handle models that are perhaps deep networks, deep learning networks, or perhaps even some combinations of neural networks and Markov chains or Markov decision processes. So in this direction, what we have started as the first step, we started looking at Bayesian neural networks. They are neural networks which have a prior on weights. And this prior on weights will account for noise or uncertainty in the measurements. And in terms of the network, what it would also produce on output is, in addition to the decision of the network, it would also produce a measure of the uncertainty, which can be interpreted probabilistically in the Bayesian sense in terms of the posterior. So what we are trying to do is we are trying to develop the basics for probabilistic model checking for such Bayesian neural networks. And that means capturing the conditioning on training data. And the hope is that over time, we can take it towards the logic to develop not just probabilistic model checking for neural networks, but also for hybrid combinations of such Bayesian neural networks and conventional transition system models. Now, this has already been applied in the context of autonomous driving controllers. So this is a pilot net, but we have a Bayesian variant of the pilot net, and we've used statistical model checking to actually evaluate the distributional shifts. So we evaluated what happens to the safety of the controller as you change the conditions, so the weather conditions. This is all based on the Chlipala simulator.
Marta, we've just about consumed all the question time already.
Okay, sorry. Okay, sorry. So this is the conclusions, and I just wanted to acknowledge, so I will leave this.
Okay, thank you. So we have so far 3 questions. Maybe we can fit them in if we risk. I'll just read the first one. All M questions, Marcel, Mohammed, and Michael. Marcel asks, can Prism handle infinite state systems?
Not directly. No, I think Prism is probabilistic model checking can only handle finite state models, but of course, if you think of timed automata, you know, they are, so probabilistic timed automata, they are infinite state systems, but they have to be reduced to a finite representation.
Mohammed asks about the possibility for changing a global variable in a synchronized command beyond Joachim Klein's work.
Beyond, can you say it again?
Mohammed, maybe you should just ask your own question if you want to unmute. No? I think a major limitation of Prism from a practical perspective is not to allow changing a global variable on synchronized command. Is there any progress/plan for that beyond Joachim Klein's work?
Okay, I don't know. I think for this, if you could ask Dave Parker, because he will be on top of, well, of how far he has managed to get through the long list of user requests.
Yeah, okay. And finally, Michael asks for a comparison against the Storm probabilistic model checker.
Okay, so what kind of comparison? I mean, the Storm model checker was constructed later, so more recently. Prism, the original Prism is already 20 years old, and you know, it was developed from a PhD student project. I think the Storm model checker was constructed by a larger team. So from the software engineering point of view, it is probably better engineered. But there is a lot of interaction between Prism and Storm. For example, there are a number of Prism case studies, and the modeling language, sometimes it is used by Storm. If you are interested, there is now a competition of quantitative model checking tools. It's an annual competition, and there are annual reports. So there are various challenges that these tools are exposed to, and then there is a report. So this is probably a very good report if you are trying to select the best tool for your specific application.
Okay, then thank you very much. And okay, with that, we should move on.
Thank you. Thank you. Sorry, I've overrun.
That's fine. If you could unshare, and do we have Martin Vechev? Yes. Martin, do you want to share your screen?
Hi, everybody. Yes, let me do this.
Hello,
hey, how are you? Let me just try this complex operation. There you go.
So I introduce you very quickly. So it's a pleasure to have the last talk in this session from Martin Vechev from ETH Zürich.
Okay, thanks. Thanks, Peter, for the short introduction. Hi, everybody. Yeah, my name is Martin Vechev. I'm a professor at ETH Zürich. I hope you guys can hear me. If you have any questions, you can just type them in the chat. And I'm very glad to be back in Cambridge virtually, hopefully physically soon. So the topic I'm going to talk about today is on certification of deep neural networks. And so I think this is, I feel this is one of the fundamental challenges, you know, this problem of creating accurate and safe deep learning models that precludes the adoption of you know, deep learning across a wide range of domains. And it's not just, you know, my academic perspective, that's also how it's also shaped by our conversations and discussions with different industry partners that we work with. So we worked on this problem ourselves in my group at ETH, as well as Many other groups around the world are working on this challenge, and Marta also, who just gave a great talk. And so you can find a lot of our work here on this address, safeaittaz.ch. This comprises all kinds of techniques, spanning verification to certified training, fairness, how to incorporate word knowledge via background prayers, and many other techniques. And so if you're curious, you can go and check it out. So just to make the discussion a little bit more concrete, because we're focusing mostly on certification here, let me consider this particular property that the community has investigated over the last 5-6 years or so, and that's the property of robustness, right, to perturbations. So here in this setting, for this property, you have the following situation: you have an image, you have an input 8, and in this example, and you have some kind of perturbations to the image. So it could be rotations, could be noise, could be brightening, lightening, flipping, all kinds of transformations that you can do. It could be captured also by a generative model, like a variational autoencoder. So not really programmatically, but learn from data. And your goal is, feed these perturbations to the neural nets, and your goal is to prove that these perturbations don't change the classification. So whatever you do to the image, up to some limit, the network is stable and classifies the input to 8. Or of course, you find a counterexample to that, and show that some of the perturbations actually change the label. So it's a very general problem. Not really so much from an adversarial perspective, but just proving stability and kind of ensuring confidence in the models. Of course, this image, this input doesn't have to be an image. Could be an audio wave where I'm just perturbing the sound, like the volume of the wave of the recording, like I raise my voice or I quiet the voice. It could be like a natural language sentence that you perturb. Could be many things. So generally speaking, it's a pretty hard problem for verification. And the reason is that it's tricky to enumerate the brute force all the possible combinations here. So you'd have, even for a simple 2-bit change on a pixel, maybe something like 2 to the 784 pixels, which is clearly 2 to the 174 images. If you have 784 pixels, which is clearly unfeasible if you are trying to enumerate this. At the same time, direct application of standard solvers like SMT solvers or mixed integer linear programming solvers do not really scale to the kind of non-linearities that neural networks have. And so over the last 3-4 years now, we've been working on solving this verification problem. And we've adopted the following view, right? That deep neural networks are essentially numerical transformations, typically some kind of affine transforms, some linear transformations, with some limited forms of non-linearity. And in the community of programming languages and verification, in this area, there is this area of abstract interpretation, and specifically a sub-area of abstract interpretation, which is called numerical abstract interpretation. And that area, focuses on reasoning about numerical programs. And so to us, initially, when we started looking at this space, we thought, well, I mean, this is just mostly applying these existing techniques to deep neural networks and proving whatever safety properties is it that we care to prove. And that's exactly what we did initially when we started working on this 3-4 years ago. We had this framework, it's called AI2, which essentially took a neural network and compiled it down to some standard language. Once you have it in that standard language, you can apply existing advancements that the community of numerical abstract interpretation has made over the last 40 years or 30-40 years. And the high-level idea is something like this. You have an input, like in our case, it was image 8, and you put a region around that image. So this captures all the possible perturbations that you can make. So in this case, is some a box, some hyperrectangle. And that box, this blue box here, is described by some symbolic constraints, like this. Well, let me just highlight it here. Let's see. There's another color. So this would be like this logical formula here, okay, which is in this case is some kind of zonotop because it contains some error symbols here. It doesn't really matter. It could be some restricted polyhedra or some other logical formula. And then what you do is using abstract interpretation, you push that formula, this initial region through. And to push it through, what you need to do is to replace the concrete layers of the neural networks, like the affine layer and the ReLU layer or sigmoid or whatever layer you're using, and to design the corresponding abstract layers, meaning defining the effect of the layers on the abstract shape. And once you do that, you can push it through and get these funny shapes here, typically some kind of convex shape here. And you push it through, and you do it in this way up to the end, where you get some output shape over here. And once you get this output shape, which is also described by some logical formula, we don't have to worry about the constraints here. You can prove your property of interest, your safety property of interest, be it robustness or be it something else. So that was our original view, but the problem, I mean, this scaled quite a bit more than existing solvers at the time, but it was still not scaling to the more larger networks. And so what has happened in the community over the last 3 years, I would say, is that people have developed some custom custom abstract interpreters targeting neural networks specifically, and not compiling it down to some basic language like we did. And so AI2, of course, by now the method of AI2 is not competitive, but the idea of using abstract interpretation still remains. So we also did that, other groups did that. And so what I can say is that essentially what happened is that a lot of the advancements can be summarized kind of in a couple of slides at a very high level, of course, because technically they're a lot more involved. But essentially what happens is that if you have this shape over here, this funny zonotop restricted polyhedra shape, which is described by some constraints. I mean, these are, of course, not the constraints that describe this shape, but there is some symbolic constraints that describe the shape. The way that you obtain the output shape over here, this formula psi, is by when you're trying to figure out what the constraints are for this output neuron here, Y1, you look at only the input neuron X1. So if you look at the ReLU function, you're only looking at this kind of dependency here. And if you're trying to figure out what is the constraints associated with Y2, you're only looking at the constraints associated with X2. And so this is how this single neuron, that's why I call them single neuron abstract transformers, work, because they kind of like look in the corresponding single neuron in the prior layer. And so that's how things developed. And so what happened was that this is the many kind of approximations of this kind that people developed of the ReLU and other activations, other activation functions. And so if you, for instance, have the input X here and have the output Y, let's say of the ReLU function, over here you have some LX and UX, which is just some lower and upper bound, which bound the possible value for the input neuron X. Right? In this case, actually, it could take negative values due to abstraction. And so your job is to actually approximate this piecewise linear function with some convex shape. And so in the single neuron view, the best convex shape that you can get is the triangle. Okay, so you just introduce a bunch of invisible points here in this blue region, but you certainly capture the green lines. Okay, certainly capture the green lines here. So you can capture the possible values of Y given the input X. Now, propagating triangles through would be nice, but it's actually quite expensive and also doesn't scale very much. And so this triggered again this kind of single neuron abstractions to where you are, propagating not triangles but some approximations of triangles, which could be boxes, could be zonotops, could be restricted polyhedra constraints, and this kind of approximations, this kind of relaxations, as some people call them, appeared in all kinds of areas in machine learning, programming languages by different groups. And if you can see here, actually, you'll probably notice that this zonotop approximation, and these zonotop approximations are custom. They are not like the original zonotop abstract domain that was introduced in, I believe, KAIST 2009. It's a bit more specialized. But what you'll see here is because this line can actually go up and this line can actually go down, there's not like a unique best approximation. And so you can actually have multiple approximations of the green ReLU. All right. But so this triggered a lot of research. Many verification tools kind of play with different approximations like this of the green ReLU. And this to the point where some people said, there was a paper by Salman and others from Microsoft Research where they said, well, the best thing you can do in terms of certification of neural networks is the triangle, essentially. So this triangle approximation is the best you can do. And they studied in this paper, they studied the different complex relaxations when it comes to like verifying neural nets. So this turned out to be useful, I think, but not entirely right, because it turns out, and that's why I'm presenting it to you in this way, that a lot of the works are actually making this assumption of the single neuron view. Okay, and so in the single neuron view, the triangle may be good, maybe best, but in the multi-neuron view, that's not true. And so if you look at, for instance, like this input shape over here, where you have x1 and x2, two input neurons, x1, x2, just like we had in the previous slide, and there's some constraints associated with x1 and x2, which form this, form some shape over here, this flip square here. If you're actually doing the triangle for x1 for y1, and you compute the triangle for y2, you would end up with the following shape over here. Okay, so that would be the best you can get in the single neuron view. But if you're actually doing consider x1 and x2 together as a constraint, you'll actually end up with something which is some shape which is actually tighter than the single neuron view. And so I think like the future of verification, essentially, if you want to get into this area, depends a lot on the multi-neuron kind of view. But of course, if you consider all the neurons together, then you also wouldn't scale. And so you need to kind of bound how many neurons on the layers you're considering when you're doing your your abstractions. So K could be like 2. In this example, we have 2 neurons, x1, x2, but it also could be 2, 3, 4. But if you go too high, then you actually wouldn't scale again. So which neurons to combine and consider jointly, how to consider them, that's kind of like an open question. We've worked on this problem quite a bit. There's this paper here that's actually on arXiv right now. It's quite recent, it's from a month or two ago, where we've generalized this idea to like other beyond ReLU functions. But this, I think, is the promising direction when it comes to like core methods for certifying neural nets. Carefully considering groups of neurons when you're transforming their abstract shapes. Okay, so generally speaking, we try to incorporate all the advancements that we make in a common framework, and this framework is for us is called the RUN. We incorporate here all the advancements that we make, be it in like single neuron abstractions or multi-neuron or particular GPU speed, GPU implementations of these relaxations. And so the framework simply works by giving it a neural network, a precondition, and some post-condition, maybe like robustness, and then you run it, and it tries to verify the property of interest. For those who are interested in the space, myself and some of my students and other people in the area are organizing this competition, the neural network competition. It was held last year for the first time, and this year again there will be another one. And people are looking at the different kinds of networks, different kinds of properties, and still it's quite a developing space. But I should say a RUN is actually quite used also by different industries, like for instance air, the automotive industry, and travel and so on.
Martin,
yeah.
Let me just interrupt to encourage the audience to start adding questions to the chat. To give you
definitely
a 5-minute ping, depending on which question time you want.
Yeah, just add questions, no problem.
Yeah. Okay.
Okay, so this is kind of the verification view, and so just so that you don't get the idea that we're only working with like noise. If you want to certify, let's say, rotations or translations to an image, let's say rotation by 30 degrees, you'd take essentially the the rotation code or the rotation function, and you would with the input 0 to 30 degrees, you take your image, and then you generate some region here which captures all the possible rotations that you can do to the image in that range, and then you can feed this shape here to the neural network and try to verify it just like before. Here I can already mention you one of the open problems, which is finding actually, counter examples to geometric perturbations. So finding, let's say, let's say I'm trying to find something like 29 degrees. At 29 degrees, we get a counter example. How do we actually find this out in the case when we have bilinear or bicubic interpolation, which introduces basically a continuous space? Is actually an open problem. It's a very basic open problem, and without solving this open problem, actually you cannot really do certified or adversarial training. So that's a very interesting thing. One last point I wanted to make before we wrap up is that certification, verification techniques are just one part of the challenge. Another major part is actually building networks that you can verify, because if you don't actually train the network in a way that you can verify it, you're not going to be able to verify much. So we worked on this problem as well. So introduced this idea about using abstract interpretation for certification, for training. And the basic idea here is actually quite, very simple, but the framework turns out to be quite applicable. So essentially what you do is, again, you do verification and you push, this shape through just like before. But now, rather than just, saying yes, no, you use this shape here that you get to train. And so what you do is you pose the following optimization problem, which is just a lifting of the standard machine learning training setting, which basically says, once you push it through in that shape, try to find a point over here, point Z, and try to find this point which maximizes the loss. Okay, so just try to find a point which maximizes the loss, and then try to find weights in the network. Try to find weights in the network which minimize this effect of this bad behavior of the loss. And so this essentially what it does is it requires you to do automatic differentiation, not through the concrete transformers like ReLU, affine, and whatnot, but through the abstract transformers that you are running here at these layers. So that formulation here turned out to be quite I think useful because it allows you to plug in any advancements in verification going forward. But and so there's various work since then which are using this kind of optimization problem with several improvements. But still, even if you do that, we are still we're still not there when it comes to building. Remember the challenge: we want to build models which are accurate and they're also safe. But when we train in this way, actually our accuracy reduces, although our certified robustness goes up. And so a lot more work is actually needed in this space. A lot more work. One of the challenges here, one of the fundamental problems that's associated with this optimization problem here, this min-max optimization problem here, is that essentially why we're failing, we believe, is that more complex abstractions like restricted polyhedral, zonotopes, and whatnot, lead to more difficult optimization problems. And then it's even though the solution may exist, it's actually hard for gradient descent to find that solution. So we studied this situation, this question, and there's a work that we published last year. I put on arXiv again, which explains. I think that's a very important thing to understand why more precise verifiers may not lead to more provable networks, which is quite counterintuitive when it comes to verification thinking. There is a lot of work that needs to be done to pose easier optimization problems than the one here. Okay. We worked a bit on this. Our groups are working on this, so I encourage you to take a look at this space. Okay, so let me wrap up. So let's have some time for some questions. So what is, I think, next in certification in general and this certified training? So what we are lacking a bit, and where are we now? Right now, right? We are at the situation where there's been a lot of work on certifying, noise-based perturbations like L infinity. But in practice, this is not something that many companies actually care about. But it's a very good thing when it comes to comparing different verification tools. It kind of sets a common benchmarks. Only recently there's been work on like geometric verification, audio certification, generative models, natural language processing, but we need a lot more, look at interesting specifications like semantic specifications, more generative model-based specifications, temporal, probabilistic, and so on. In terms of verification techniques, I would say in order to scale this to realistic networks, you need, the whole community needs to look at more like multi-neuron abstractions, like the one I mentioned to you. and integrations with GPU, because that can lead to massive speedups when it comes to verification. Really scale it much further. In terms of applications, so far, community has focused mostly on classification, but there's so many other models that one can look at, and from natural language processing, hybrid systems, many others. And the important bit here is that when you do that, at least in our experience, when you look at, let's say, for instance, recurrent networks, the abstractions and the convex relaxations that you develop in that setting are custom to those networks, right? And so it's not as trivial as just applying existing techniques. So we need more of that. And finally, as I mentioned already, verification alone is not enough, right? Unlike kind of traditional theory for constructing programs, or even in cryptography for creating secure schemes, in machine learning, there isn't really a general method to construct programs that satisfy given properties. Much of the work goes through this pipe of gradient descent, which is a limitation. And so what we need is better training techniques which produce simpler optimization problems, okay, for gradient descent to solve. And we also need, network architectures to be much more verification aware. Right now, I mean, a lot of these network architectures are just designed for high accuracy, but they're not aware that some verification will be done after. So this is what I want to tell you and some of my thoughts. Of course, this is a topic we can talk about for a long time. Oops, let me skip this slide in the interest of time. At ETH, we have a course that we teach on this topic. So it's a full-blown course. How to create these safe, fair systems, provable, and so on, both deterministic verification, statistical verification, and so on. And so it's been going for the last actually 4 years now. And the course is actually on YouTube due to various people asking about it. So you can go and check it out. Thank you very much. And I hope I didn't run out of time too much.
Okay, thank you very much. So we have a couple of questions. Maybe it's simplest, as we have a few minutes, if I ask them to just unmute themselves and ask. So Marco, you want to go ahead?
Hello? Am I working?
Yeah.
Right?
Yeah.
Okay, great. So you mentioned earlier that SMT solvers can't handle the non-linearity of deep neural networks well. Do you think a delta complete SMT solver, such as DReal, for instance, could handle this non-linearity?
I don't think a pure SMT solver will be able to handle the kind of networks that we need to handle. I think all the successful applications of complete methods would typically require some integrations with convex relaxation and approximations that kind of showed you. And that's, I think, where the SMT community is also looking at. I think DReal is very interesting, especially in the combinations with hybrid systems. But I think a lot of if you look at the way things are going with this multi-neuron, it's really about very careful relaxations with very careful combinations with complete methods. So I hope this answers your question.
Okay, thank you.
Yeah. So there's another question by Supratik. It says, are there plans for integrating SMT solving techniques like Reluplex with abstraction-based techniques like deep poly? Yeah, I believe, so there is in the general verification space, we didn't get time to talk about it, so you can check out the course. So there I show combinations of like mixed integer linear solvers with abstraction techniques. I think that's a very promising direction. And I think Clark Barrett's group at Stanford is looking at, and Guy Katz in Israel is looking at, Hebrew University is looking at kind of these integrations with SMT with abstract interpretation. I think it's very promising, very interesting space.
Okay, do we have any further questions?
Yeah, there's one more. Okay. Oh, yeah, no, thanks.
Oh, that's a very unit question.
Yes.
Okay, then thank you very much again.
Thanks a lot. Thanks for attending.
So I'm not quite sure what the protocol here is, but I think we can create some breakout rooms if Martin or Marta or Hongseok or...
Okay, welcome back. The first speaker of this next session is Adam Chlipala. Adam has been a faculty member at MIT since 2011. His research is on machine-checked proofs of software and hardware systems, about which he has written a book on an introduction to the code proof assistant called Certified Programming with Dependent Types. Keep in mind that you can pose questions on the chat at any time during the talk. And at the end, you can raise your hand and I will call on you to ask questions in your own voice if you don't mind being on the recording. Adam, please.
Thank you. So it's great to be here telling you about correct by construction cryptographic arithmetic. My talk is going to overlap a lot in application domain, at least, with Karthik's talk from yesterday. And it's joint work with a few students listed at the bottom here. Let me still review some of the background that's in common with Karthik's talk. Think about what happens every time you do you load a web page where you get a little lock icon in the browser. There's a server somewhere you want to talk to that has a public-private key pair and a certificate issued by some authority. And your browser starts communication with the web server by going through a key exchange to establish a shared secret. But before proceeding, the browser wants to know it was talking to the server it meant to talk to. So it's not ready to use this symmetric key yet. Stay tuned for that. First, we have to get a hold of the public key in the certificate and have the server produce a digital signature that shows it actually knows the private key, and it is the server we thought it was. And after we're convinced about that, we can go into the main loop of byte stream communication using the symmetric key that we agreed on. So those first two stages are applying public key cryptography. They only need to run once per secure web browsing connection, but you can have many connections loading a single web page. So their performance is still important, but it's pretty challenging to balance performance and correctness for this domain, where one of the biggest sub-challenges is doing arithmetic on really big integers modulo really big prime numbers. Sounds simple, but it is a remarkably deep area of optimization challenges. Luckily, there are a whole bunch of crypto libraries out there already, and we should just be able to use them, but it's still pretty difficult to come up with a comprehensive library that covers all the cases people care about. There's a moderate set of algorithms for cryptographic primitives that are standardized in, say, different internet standards, moderate set of different prime numbers that are used as key parameters to those algorithms, and then a few interestingly different kinds of hardware architectures that we want to run our code on. What I was shocked to learn before starting this project was that the state of practice was when you want to explore a new element of this three-way Cartesian product, you get an expert to rewrite all the code from scratch in C or assembly. So we figured it was worth trying to find a better, more automated way without giving up on performance. So we developed basically a domain-specific compiler called Fiat Cryptography, which can take in your parameter choices from that kind of menu and generate your code for you. And this compiler is implemented and proved in the Calc theorem prover. It's been adopted for a number of small but important pieces of code in projects that actually overlap a lot with the ones that Karthik was talking about, including parts of the TLS implementations in both Chrome and Firefox, Linux kernel module, and a number of blockchain systems. So what exactly are we trying to prove here? How do we fall within the larger area of correct by construction cryptography, which has been represented in a number of talks already? The gold standard here is some kind of security property, like you can't produce a convincing signature fast enough if you don't know the secret. Protocol verification connects that kind of property to mathematical algorithms, which might, for instance, work with huge integers that we don't know how to fit in the registers of commodity processors. And then we might go through an implementation synthesis process that gets us some commodity assembly code that is able to implement that algorithm efficiently. So our project is just in the bottom part of this picture. though we're interested in connecting to protocol verification as well, and several other projects like Everest that Karthik talked about have done that kind of connection. Just focusing on the implementation and synthesis part, though, we're looking at what's called elliptic curve cryptography, where we operate on two-dimensional points. And there's a counterintuitive optimization where these are actually encoded as four-dimensional points at runtime, just so that we can avoid needing to run as many expensive instructions like division and mod. Those would totally kill performance, so we can avoid them in a counterintuitive way with more coordinates. And then each individual coordinate is so large, it's not going to fit in one of our registers. Even say 3 of them won't fit in one of our registers. So we need to break coordinates into sets of digits, which themselves fit in registers. And then we need to compile finally this code, which is close enough to a fit with the instructions we have on hardware to get out low-level code that, for instance, uses fixed precision integer types instead of infinite precision integers. And we have Coq proofs associated with each of these stages, and they all compose with each other to get the right kind of pipeline connecting what I'll call the whiteboard level spec with your efficient C code. Here are 2 examples of the outputs of that compilation pipeline for different parameters. Actually, the only difference between these 2 runs is that one is targeting 64-bit processors and the other 32-bit. I've intentionally chosen these the text here to be small, so you're not tempted to try to read and understand all of it. The main point is it's at least moderately intricate, and it's interesting how big of a difference in the code you get just by choosing a different kind of processor that you're targeting. So what are the differences in how code is generated, or how experts had previously been writing it by hand? The key element of all this is that counterintuitively, when you choose a different large prime number to be your modulus of arithmetic, it can have a big effect on the algorithms and data structures that you choose for your code. So as an example, let's think about a class of primes called pseudo-Mersenne, which are large powers of 2 minus small constants. As an example of an operation we want to perform, let's talk about modular reduction. In particular, let's say I just multiplied together 2 numbers in this prime field. Before we consider the modulus operation that will come after the multiply, this naturally takes twice as many bits as we needed to represent any one of the 2 operands. So let's divide that large output of multiplication into the lower order bits x and the higher order bits y. And we'll shift the higher order bits into position, multiplying them by 2 to the k here. And now I want to run mod to shrink this back down to fit within the original size. Well, let's do a little bit of algebra. I'll subtract and add this constant c in a certain place and then distribute plus over times. And now I notice, jackpot, the modulus itself appears as a subterm of this formula. Modulus, of course, is congruent to 0. So I can cross that term out. And now I have a cute recipe that performs a mod operation using just a plus and a multiplication by a constant, which are very fast operations compared to mod instructions on commodity processors. This cost savings is enough to motivate careful choice of primes like this one behind, say, internet cryptographic standards. So let's look into more of the details here. Let's say I have the same prime modules I just talked about. I've done a multiply. Result is naturally 510 bits wide, and that actually winds up split across 8 different 64-bit registers. And the higher order half of those, we can see in that formula, the lowest line here, that reassembles the big number by weighting those digits appropriately, adding them together, and then shifting them by 256 bits. Oops, that's 2 to the 256, not 2 to the 255. So we are ineligible for the optimization I just talked about on the previous slide. So basically, no one uses this representation in practice. Instead, if you're targeting a 64-bit processor, you will typically break your 510 bits into 10 digits of 51 bits each. And now we have a 2 to the 255 in the right place. And this is very fast. The weird thing about it is we're using 64-bit registers, but not even using all the available bits in them, because this higher level optimization only applies in this case. If we're targeting a 32-bit processor, we'll take each of those 51-bit digits and split it into 2 digits of 25.5 bits each. Unfortunately, this year at least, our processors aren't giving us fractional bits, so instead we'll just alternate between floor and ceiling operations to compute to compute how many bits each digit should be given. And so then we get this formula here. And this is now the champion representation on 32-bit processors. Even though it's even weirder than the last one, it doesn't even use the same number of bits per digit. So we can see for a single algorithm, there are already at least 3 reasonable data structures we could choose, which then imply different variants of how the algorithm gets compiled. So what we decided to do was create one library that is parameterized on a choice of a data structure, basically, and will then output fast C code for you. And the library itself is implemented in Calc and proved. And in more detail, we've built a generic library of arithmetic operations as pure functional programs. Proved those once and for all. We can use partial evaluation to specialize them to parameters, most importantly, the big prime modulus and the choice of digit representation of numbers. And this creates nice flat functional programs that already look a lot more like C than the code we started with. And then we can do some verified compiler stuff, including abstract interpretation to infer bounds for variables. And we can get out literal syntax trees of pretty simple sublanguages of C and others like Rust. So each of these phases has proofs in Calc, and they all compose with each other. And then that composition composes with some of the higher levels that I showed you on an earlier slide. So as an example of what we stock our library of arithmetic algorithms with, let's think about multiplication for a smaller modulus, 2 to the 127 minus 1. Here, let's say we split each number into 3 digits that are reassembled into big numbers with the formula shown here. I naturally do multiplication by computing all 9 cross products of these 2 sums, which I've arranged suggestively here in columns. So we're actually going to compute 5 different digits as the naive output of multiplication. And we get each digit just by adding down each column. They've been set up so the powers of 2 are very close to each other. So this is a straightforward operation. And then this formula shows how we reassemble the big number out of the output here. But I want this to be a modular multiplication, get it back down to fitting in just 3 digits, not 5. So I take advantage of the fact that where I have a 2 to the 127 factor in there, that's actually congruent to 1 in this modulus. So I can move those 2 digits at the right side to be added into some of the other digits earlier. And now this is our final multiplication recipe. You can imagine building a functional program that is the generic version of this for different moduli, different ways of dividing numbers into digits. So we did that. We proved it once and for all. Same for lots of other arithmetic operations you need in crypto. So then we have our multiply routine. Some of its inputs can be viewed as compile time, like the choice of digit bit widths. The rest can be viewed as runtime, like the particular digit values. We can just specialize this to particular choices of the digits and then apply algebraic simplification to reduce it into a version that no longer has most of these overheads of generality. The cool thing about doing this in a general purpose proof assistant like Calc is that both these steps are pretty routine. Specialize is just partially applying a curried function. And reduce, well, term reduction is one of the most fundamental operations that pretty much any proof assistant is prepared to do. So we can get built-in Calc tactics to do this algebraic simplification for us. Almost. They will do the job, but they can turn out to be unbelievably slow and memory inefficient. So we did decide to invest in creating our own alternative to the built-in reduction after the first version of the tool that used built-in reduction. And briefly, we're using a technique called proof by reflection. We've built a tactic. Tactic is a proof-producing proof step box. It takes in a list of proved algebraic rewrite rules that should be used for simplification, as well as a term to reduce, and then outputs a new term along with a proof that it's equal to the original, so long as the rewrite rules were all proved correct in terms of equality. And on the inside, this works by feeding in a set of rules to this tactic. The rules are reified as syntax trees within the logic, and they're then fed into a generic reducer, a functional program that we wrote and verified once and for all, which is parameterized on rules. And then we reduce the reducer into a specialized reducer. The reduction process is correctness preserving, so then the output of this is also correct. Then you can feed in your particular term, reify it in logic, use it on the reducer, produces another syntax tree for the result, and then we basically apply an interpreter to that to create the final output term of this process. And this basically takes some of the work that was being done by Calc in an unproved way within the OCaml implementation of Calc and turns it into formally verified algorithm within Calc, which has a number of advantages in trustworthiness and, in this case, performance. So as an example of what comes out of this compilation, let's think about one of the cases I showed you before, where we're in a particular prime field and we're using 25.5 bits per digit out of 10 total digits. The first definition of a function called W on this slide expresses that digit splitting strategy by a function that assigns a weight or coefficient to each digit based on its position. Then the next command, that starts with the word example, is asking to synthesize a multiplication routine that takes in 10 tuples of integers, f and g, and is supposed to return fg, a new tuple of the same type, such that if I evaluate that tuple according to the meaning of these tuples, apply mod to it, I get the same answer as if I evaluate the two inputs, use the normal whiteboard level multiply on them, and then take the mod there. That's just another way of saying this is a correct implementation of multiplication. And this is the kind of output that arises. We get a functional program like this, along with a separately checkable proof of its correctness according to that spec. You can see it has a fair amount of magic numbers and other details that we can be glad we didn't have to come up with ourselves. So that's probably the biggest step of this process, but we're not done yet. We need to take an expression like that and get it down to C code somehow. So imagine this is the expression that came out for one of the digits. It has two free variables, x and y. We reify this to a syntax tree, and then we start doing classic compiler phases, which are all going to be proved. On the example I've shown you here, that expression shrinks a lot. Then we can flatten that to introduce names for all the intermediate computations. And then the part that's most different from, say, GCC, we're going to infer bounds for all the variables, which are actually infinite precision integers here. And this bounds information will let us assign them into C integer types. So let's assume we know going in that x and y are bounded above by 2 to the 51 plus 2 to the 48. We push that through and infer a bound for each intermediate variable. And then we notice in each case, one of these bounds says we're small enough to fit in 64 bits, but too big to fit in 32 bits. Therefore, let's give each of these temporary variables a 64-bit integer type. And in general, we might spit out one piece of code that mixes 32-bit, 64-bit, even 128-bit integer types based on what the bounds analysis tells us. And again, all these phases are proved, and they compose with each other as well as proofs of earlier elements of our pipeline. So the library is a few tens of thousands of lines of code, including proofs and including parts that really make sense in some sort of mathematically oriented standard library. And we wrote a script to make this as easy to use as possible, where you can just tell it what prime number you're interested in as your modulus, if you write it in a suggestive way of adding and subtracting powers of 2. Then we have a heuristic that suggests a good digit breakdown. This script isn't trusted, though, because any digit breakdown leads to correct code. It just might not be fast. So then we needed a lot of test cases to run our compiler on. So the way we decided to get those test cases is we scraped a popular mailing list about elliptic curves, found all textual sequences that seemed to be describing primes. That gave us about 80 primes. Only a few of these turned out to be really bad ideas that actually nobody knows how to implement efficiently. So our compiler might time out on those because it generates ridiculous amounts of code. But then most of them worked fine. So this is a graph comparing our compiler results on those from the previous best known generic implementation of finite field arithmetic, the GNU multi-precision library, which offers two different modes. One that makes an effort to avoid allowing timing to reveal details of your numbers. That's important for crypto routines. You don't want your key to be leaked by timing. So we compare against both of their versions with and without this security measure. And the x-axis is the size of the prime, y-axis is running time on a simple benchmark. You can see we're typically in the neighborhood of 5 to 10 times better than this other library, even if it gets to use the insecure versions of operations, whereas ours follow the right security guidelines. That was targeting a 64-bit desktop machine. We also did automatic compilation for a 32-bit mobile phone with an ARM processor, and we see pretty similar results, often in the neighborhood of 5x or better performance, and we have much stronger formal guarantees, of course, than a traditional C library like GMP. We also have good performance results on the specific widely used prime fields for internet standard protocols like you use with TLS here you can see our generated C code, depending on the C compiler, it's always doing better than the C code in OpenSSL. It can get within about a factor of 2 of the handwritten assembly code in OpenSSL. And this is pretty typical. We tend to see about the best known C performance for all the elliptic curves running our compiler, where previously all that stuff was handwritten. So the next steps for the project include trying to close that performance gap. It's also a trust gap because at the moment we output C code and we'd rather be getting theorems about assembly code. So an approach that we're exploring there is building an equivalence checker that takes in an assembly program along with the output of our higher level pipeline and uses kind of SMT solver style techniques, but written and verified inside of Coq to establish that the two give the same performance. So we can port our confidence and correctness from the end of our current pipeline down to that hand optimized assembly, maybe also combine this with new compilation strategies that can produce that assembly automatically. We're also interested in extending our code generation approach to work for higher level parts of crypto libraries. I didn't emphasize it too much here, but the tooling I just told you about only generates straight line code. Of course, there are routines elsewhere in crypto libraries that need features like loops and function calls. So we're looking into ways of supporting those as well. And so then a medium-term goal kind of shared with the project that Karthik was talking about is to create a complete enough TLS implementation that's derived in a correct by construction automatic way from a reasonable looking functional program that isn't cluttered by optimizations, where instead the compiler is introducing the optimizations and everything's proved correct and you get a nice end-to-end guarantee connecting your whiteboard level version of the crypto library down to assembly code that has good performance. All right, so I'll just stop here with the URL to our project. As I mentioned, a number of open source projects have had good luck applying our tooling even without bugging us. You get a command line compiler, you don't need to know anything about Coq, just pick different prime numbers and data structures and C code comes out, or Rust code, a bunch of other options. Be glad to hear about any experiences using it. Thank you.
Thank you, Adam. So questions for Adam, you can speak.
Hi. Yeah, really great talk, really interesting.
Thanks.
I want to go and play with this stuff. So you say you're targeting kind of curve arithmetic, which makes sense. And obviously I appreciate your kind of medium-term goal is TLS. If you're looking at curve arithmetic, have you thought about, is there any plans to look at some of the post-quantum schemes? I'm specifically thinking here of something like SIDE, which is isogeny based, right? So like, with the thinking that if you've already got a field arithmetic and curve arithmetic implemented, then you're like 2/3 or something of the way there. So would that be a thing that you'd be looking at doing in the future? Because obviously this feels very focused in terms of primitives on ECC. And I was wondering if, are there any other primitives you're looking at or,
So there's a little bit of a challenge with going to our understanding of the major options in post-quantum. Maybe it was only lattice-based approaches we asked people about. The problem we ran into was the work to get there was split between too easy because we already did it and too hard because it involves explicitly probabilistic reasoning, which has had no role in this project so far and could easily turn into several PhD theses worth of work. So at that point, we decided to focus on getting a TLS library instead.
So my experience with Psych, I should say, specifically, has very little probabilistic components. I think this is true of some others, but it has a bit of randomness, but not really much, and most of it is doing some arithmetic on doing isogeny arithmetic on curves, which feels closer in scope. I was doing some work last year. Anyway, I was frustrated at some point last year that GMP wasn't verified and also wasn't very fast. And so it's nice to hear that someone has gone and done field arithmetic in a fast verified way. So it just sort of feels very close. Because I think doing some of this work with some of the more probabilistic schemes is tricky from what I understand.
How do you spell that algorithm you were just talking about?
Sorry, I'll type it in.
Thanks.
Psych.
I'll take a look at it in the chat after we finish here. So thanks. Maybe we can context switch to the next question.
Andrea, do you want to speak?
Yes. Hi, thank you. Very interesting. I just wrote that looks much more broadly applicable rather than only to cryptography and algorithms. And my question was whether you intend to apply to zero-knowledge cryptography, or similar approaches that have been applied to zero-knowledge. Thank you.
I am very far from being an expert on zero-knowledge proofs. I don't even know what a typical algorithm looks like. So unfortunately, I don't think I can answer that question without more of a setup. If it uses finite field arithmetic, it should be able to reuse these results, though.
Okay, thank you.
Okay, we have time for more questions if there are any. I'll ask one, giving everyone time to gear up to more. I was wondering, for people who are not as deep into this as you are, what are the lessons learned from this project? If I wanted to do something similar, correct numeric things, but in a slightly different domain, what can you teach me at the high level that would be useful?
Sure. So I think one lesson is that if you try to apply scientific induction to lots of programs being written by hand in C, then it often turns out that the main ideas behind those optimizations can be abstracted into fairly natural, pure functional programs, and then composed with generic partial evaluation. And you can get back the efficient C code while being able to reason at the higher level for kind of the essences of the correctness of the optimizations that are being used. And so it's worth investing in partial evaluation tools. And it's harder to see how to build tooling to automate the process of designing your nice high-level functional code. But I think it's worth devoting human labor to that part for problems where you spot enough regularity.
Okay, thank you. There is Victor, do you want to speak? I'm having some noise. I'm going to mute myself.
Sure. So thanks, Adam, for the nice talk. I wanted to ask if you know what additional optimizations take place when converting the C code into assembly by experts.
Yeah, my understanding is it's all pretty specialized to details of particular lines of processors, and people are by hand doing a combined register allocation and instruction scheduling to find all the details of the arithmetic pipeline and everything in the processor and get it to work just right. And today it is not clearly known how to do that automatically, even if you ignore the formal methods part. So we're hoping to build an equivalence checker so we can take advantage of it when someone figures that out.
Okay, thank you. Then your approach makes perfect sense.
Okay, great. We have probably time for another question if there is any, and if there is no more, we can try to switch to the next speaker. Last call. Leonard, do you want to speak or do you want me to read the question?
I can say, any plans to connect this to some correct hardware synthesis tool that you may have at MIT?
Yep, we're working on it. It's almost done.
FPGA or
but there are two ways to go there. One is you're verifying the software that you then run on correct hardware and you know everything works. The other is you're trying to generate a circuit version of the hardware. It's the first one that almost works. The second one would be cool. We haven't tried it. We haven't even thought much about it yet.
Okay, cool.
Great. Thank you, Adam, for a great talk.
Thanks, everyone.
Jade?
Hi, can you hear me?
Yes, we can hear you.
Should I share my screen?
Absolutely.
Thank you. Can you see my screen now?
Yes.
Okay. Shall I get going? Or?
Oh, just 1 second. Because we are really 1 minute away, and if someone is tuning in just for your talk, I want to start on time. I'm going to do the introductions and then you go. Okay, then our next speaker is Jad Aglov. Jad is a distinguished engineer at ARM and a professor at University College London. She has done extensive work on memory models, and she's going to tell us today about the ARM memory model. Please.
Thank you. So I'm going to focus on the work I've done at ARM related to the memory model in this talk. So ARM develops what's called architecture specifications. They describe the envelope of allowed and forbidden behaviors that all ARM implementation must adhere to. And another way of seeing it is that the architecture describes what software developers can rely on. So as an example, I chose a litmus test because that's what I understand. The following message passing behavior is allowed by the architecture. So I'm going to explain briefly the syntax. We've got the initial state where we give shared addresses X and Y. The first thread P0 is writing the value 1 into memory location X and writing the value 1 into memory location Y. The second thread P1 is loading from Y and loading from X. So if you understand Y to be a flag, P1, the intent is that P1 is woken up by the writer P0 raising the flag, putting it to 1. And the hope is that this load of the data X is going to receive the new data. The question we're asking here in the final clause exists is whether there's a situation under circumstances under which the reading thread reads the flag, yet reads the stale data, which was initialized to 0. So within the ARM architecture group, I'm in charge of the memory model, which aims to explain whether such concurrent behaviors are allowed or forbidden. So more specifically, since 2016, ARM has been focusing on formalizing the memory model. It's an effort that's been started by Will Deacon. And to write our memory model, we use the cat language. That language drives a collection of tools. One of them is called HERD. It's a simulator that takes as input a formal memory model written in cat and a litmus test like the one I showed, and returns all the allowed behaviors of that test under that model. It's accompanied with 2 other tools. One of them is called DIY, that generates systematic families of such litmus tests. And the litmus tool then allows you to run those tests on hardware, on silicon hardware, deployed hardware. As an aside, those are not my tools. That's very much a tool suite that's been developed jointly with Luc Maranger, and simply the tool suite would not exist without him. So we upstream extensions, by we I mean ARM, upstream extensions to the model and the tools regularly, and our landing page is over here. And we've also written a number of tutorials on what we do with the tools and how to use them. The timeline of what we've done so far is as follows. So we'll upstream the original V8.0 model. V8 corresponds to the current state of the architecture in 2017. And later when I joined, we extended the model to a feature that's called memory tagging that allows a programmer to guard certain accesses to certain locations with a tag or color. And then people who want to access that same location have to show that they know which tag has been used, thereby giving some protection to shared memory accesses. We've also extended the model to mixed size accesses, by which I mean, imagine a case where I do a long store, say of 64 bits, and a small load of 32 bits, or the other way around. What is the load to see? Which half, if any, of the long store is it to see? And we've also upstreamed alternative definitions. So the original model is very much written in axiomatic cat in terms of partial orders and relations, as I'll show in a second. But conversations with ARM partners demonstrates that not everybody is well equipped, I guess, to understand those definitions intuitively. So we produced definitions that are phrased in terms of total orders that seem more accessible to some of our audience. And the work in progress, which I'll touch upon in a minute, is related to page table concerns. So here are pointers to where we distribute our tools. We also have a web interface that's over there. And here are the blogs I mentioned. So I've just recorded them for your reference for later. So I'll show briefly one of the tools, the herd simulator. So we've looked at this test before. It's the message passing example where the writer P0 updates some data X, sets up a flag to wake up its neighbor P1, and in the hope that the neighbor P1 can then start work on the updated data. And we've said before that the scenario where the reader is woken up and yet only has access to the stale data is allowed by the architecture. To forbid this, if you so desire, you need to use what are called, or you can use a number of synchronization primitives, some of them being fences that I've used here, DMBST and DMBLD. So DMB is for data memory barrier, and ST says I'm ordering stores, whereas LD says I'm ordering loads. And so in this case here, the presence of the barrier between the two stores ensures that those can't be reordered. And the LD here between the two loads ensure that those can't be reordered, thereby forbidding the unfortunate scenario where you get the flag but read the stale data. So I'll show you what it looks like in the simulator. So can you all see my browser?
Yes.
Okay, good. So you recognize the message passing example, and in this window here we've got the CAD file. So that's the formal model in which we describe the part of the architecture that relates to concurrency. So if I click on this button here, I'm asking the tool to tell me whether that final state here is reachable under the model, and the answer is that yes, we can. That this final state is reachable, and then it gives you a number of drawings that show you how you can reach those final states that are listed here. If, however, I modify the test as I've done here to use the fences we've talked about on P0 and P1, and again run that updated test against the model, it tells me that now I can't reach that unfortunate final state anymore. So I've successfully synchronized the message passing behavior. So at a high level, the way the ARM memory model is structured is we have a number of axioms. Two of them are so-called visibility axioms. So the internal visibility axiom gives you a sanity check over which values can be taken by a given memory location. And the external visibility one states which local orderings must be respected. So for example, the fences I've used, their behavior or their ordering power is embodied by this axiom. And formally, those constraints forbid certain shapes in program executions, more precisely cycles. So those are much like the drawings that the web interface shows you, just a little prettier, I suppose. So you can see here, so each box is the semantics of a thread. So you can recognize here the write of the data X, the write of the flag Y, here the read of the flag and the read of the data. And so the ARM memory model is what's called multi-copy atomic, which means that each communications between threads counts towards the order, and the order is called ordered before. So those are the green arrows here. If we're looking at the semantics of the test where we don't have any fences, then there's no constraint of ordering between the two writes, the write of the data and the write of the flag. And again, there's no constraint of ordering between the read of the flag and the read of the data. So that execution here, there's not enough order to forbid it. I don't have a cycle. If, however, I insert the fences we've talked about, then I create local ordering between the two writes on the writing thread and two reads on the reading thread. thereby creating a global green cycle, an ordered before cycle, which forbids the execution. Right, so now I'm going to move on to very briefly touching upon the extensions related to page table. That's work in progress with Luc, who I've mentioned before, and my colleague Nikos, who's in ARM research. So in the previous examples I showed, we assumed that X and Y were physical memory locations, but that's not usually how one interacts with shared memory. Usually one interacts with virtual memory addresses rather than physical memory directly. And the mapping from virtual addresses to physical locations resides in what are called page tables. So page table translates the virtual addresses that are seen by software into the actual physical locations used by the hardware. A page table entry in turn holds a flag that indicates whether an entry is valid or not valid. If the entry is valid, then the page table entry will give you the physical location that corresponds to the virtual address. If the flag isn't valid, then accessing a virtual address via that page table entry will raise what's called a fault. So to model page tables in our tools, we added several features to HERD and the CAT model, including a new notion of accesses to page table entries and a new notion of faulting event and the ability to ask whether a litmus test can fault. So in practice, it looks like this. So it's again a variant of the message passing example, but that uses page table entries. So in the initial state, I initialize the page table entry for the virtual address X, so that's pt_x here, to a tuple. So the tuple says that initially that page table entry is invalid. Therefore, trying to access it should raise a fault. And that even though it's invalid, it still points to the physical address phi_x. So with that first instruction on P0 here, I'm updating what's in X2, meaning the page table entry for X, to a new value that's contained in X1. So in X1, I've set up, sorry, I'm giving a valid entry, but the valid bit here is set to 1. And I decided to point to a new physical address phi_y. So with that first instruction here, I'm updating the page table entry for the virtual address X to a new valid entry that points to somewhere else in memory. And then with those two instructions here, I'm setting up, I'm raising a flag that's called Z, so that my neighbor, the reading thread, will see the flag Z. And the question we're asking here is now, if I do a load of memory of the virtual address X, am I going to see the old page table entry? So am I going to fault, or am I going to see the new one, which then will lead me to access the physical location phi_y? All of this here is what I've just said, but in writing to help for later, if that's useful. So as you can see here in the final state, we have that new syntax here that says, is it the case that, is there a scenario under which the initial load, the load of the flag, can see the flag being raised, and yet we can receive a fault at label L0 here relative to the virtual address X. So here's the execution that corresponds to that final state. So the answer is that yes, this behavior is allowed by the architecture. So the intent is not to explain that drawing in detail, just to highlight the fact that we now need a new set of events that explain how we have to read the page table entries for each accesses, and then decide whether we perform the physical access, or on the contrary, raise a fault if we read an invalid page table entry. A big part of our methodology also consists in testing hardware that allows us to probe whether the intent that described by the architecture has been correctly implemented. That also allows us to debug our model as we progress in our understanding. So that's via the tool that I mentioned before, the litmus tool. And so to run those page table tests, we had to extend our litmus tool so that it now piggybacks onto a framework that's called KVM unit tests. And we also have the ability to run those tests bare metal. All of the extensions to the tools are already online if you fancy having a go and trying to run those tests. So now I've left quite a bit of time to share observations from my last 3 years at ARM. I've also asked a number of my colleagues to share comments and observations on their experience with formal methods in general. So I'm hoping that this will raise discussions, and don't hesitate to interrupt me. I should have said that much before, but don't hesitate to interrupt me as we go and as I share those observations. So first set of observation is on architecture. So architecture is really the interface between hardware and software, and therefore architecture design requires to understand, on the one hand, what software needs. So for example, if we're making changes to the architecture, are we enhancing or on the contrary, breaking higher levels such as C++, Linux, and others? And the other side of the coin is we need architecture design requires to understand what hardware permits, and that's in our case across the whole ARM ecosystem. So regardless of which hardware vendor we're talking to, the architecture needs to embrace the behavior that's exhibited by hardware. Therefore, architecture specs are records of intent as well as record of behavior. And tooling to record and analyze intent would be most welcome. That's one of my experience of the last 3 years, is that recording intent to start with, and then recording intent in a way that's unambiguous is quite rare and not easy. And so of course, formal models and tools would be useful to help with that. And indeed, that's what we're doing, trying to do with the memory model. But the caveat is that those tools and methodologies have to be intelligible to people who don't have a formal background. So my experience of doing that exercise with the memory model is that those models are not easy to understand, to use, to maintain, or to teach. And a thing that helps in our case is that the models are executable, and their rendition to English as appearing in the ARM spec is almost one-to-one. So that helps quite a bit. Another observation I have on modeling is that at the moment is very much a small group of people reading the spec, chatting to designers, testing hardware, and coming up with formal models to the best of our understanding and knowledge. Needless to say, that's not scalable. We have plenty of features that we need to catch up on. And so as a way forward, we of course welcome collaborations. There's just there needs to be an understanding that the threshold for what done means is quite different, or can be quite different, between academia and industry. Finally, on testing and verification, so we've managed to deploy our litmus tests methodology so that we can test RTL designs now. Another negative way of seeing it is that we only do testing. I've put it in quotes here because there was already a lot of hard work to deploy, and we've had quite a bit of success. But the number of generated tests is way too high to run realistically the whole lot of them pre-silicon. And so ways to assess how to intelligently pick tests, or to assess the coverage of a set of tests, quantify completeness, or on the contrary, the lack of completeness, would be once again welcome, with again the caveat that we need to be able to communicate to people who don't have a formal background. So now I'm going to present a bunch of observations from colleagues, unless there are already questions or comments on my observations.
I think you can finish.
Okay. So I've interviewed some of my colleagues on their thoughts. So on to start with on the memory model, so that comes from my colleague Nikos. There's a recurring discussion about getting rid of weak memory models altogether and go towards stronger ones. So we'd like to reiterate the fact that this is not the direction that ARM is taking. And rather than making the model stronger, our goal, our current goal and intent is to ensure that the model, as weak as it is well-defined and formalized. And we hope that this definitions and formalization in tandem with the tools that I've presented that allow to experiment with the model will allow our ecosystem to navigate the trade-offs between performance, which the weakness affords them, and ease of programming, which may be somewhat hindered by the weakness. As a sort of opening perspective, we will need similar effort, semantics effort going on for speculative execution, for example, to detect and protect against side channels. So that observation about semantics for speculation is echoed and sort of made even wider by Lee Smith, who says that generally we will need formal models of what security means. So not only speculative executions, but for example, privacy vulnerabilities, so that we can then envisage having proofs that various levels of the stack guarantee those security properties, but we need to start by defining them. And somewhat as a similar point, but not quite the same point as the one I was making about we need to be able to communicate with non-formal people in ways that are intelligible. He makes the point that even if we have all of this at hand, we will then need to find implementations of provable technologies that are that we can actually deploy. And that goes hand in hand with observations from Katalin Marinas on the feasibility of formal methods. And I should have said that all of those colleagues are people who are not necessarily formal people in background, but have a keenness to use formal methods and to learn more. So Katalin makes the observation that models may only cover, of course, a small part of the real system's behavior, and that the correspondence between the model and the system is rarely assessed, or requires constraining your real system to a less efficient version, i.e. to not the real system. And finally, he observes that using formal methods is not easy. And so if they can't be brought up to be on par with the real system, we're not entirely sure the entry cost is worth it. And that's, to conclude, observations from Wildikon again on the idea of verifying what he called real-world systems. That's why I put that in quote. So he kindly lists a bunch of assumptions that would require removing to be able to claim verifying real-world systems. So I won't go through all of them, but they're recorded here. I wanted to finish with two verbatim quotes from him. So he makes the remark that he wouldn't mind even waiting a long time, 3 months or so, for a given solver to come back with a useful answer at the end. But at the moment, it feels like we're quite far away from this. And finally, he, perhaps a bit pessimistically, but still an interesting observation to make, he observes, he's now at Google, he observes that the term formal verification at the moment is making a lot of noise in the industry. And I echo the observation from my experience at ARM, and various papers by Byron Cook or Peter Hunt, for example, echo the observation. And so he would like us to make the most of the current opportunity, just in case the funding and or the interest from industry dries out. So there you go. Those are my observations. I'm quite happy to take questions or comments. Thank you.
Thank you very much, Rod. Sanjiva, maybe you can.
Should I stop sharing my slides or? So
Up to you.
Yeah, I don't mind.
Well,
so that then we can see people. Hi.
Thank you so much for this talk. It's really very interesting, and I really liked your comment that architectures express intent and not just behaviors. The question, I was also reading recently an account of how Tony's work on CSP so greatly influenced very many detailed architectural decisions made by INMOS when they were designing the transputers. And so that sort of brings to mind, what are the kinds of suitable abstractions that one should look at the architectural level, so that you can look at a larger space, a design space, rather than a particular decision which has been implemented. There's a context I'm asking this is because about several years ago with colleagues of mine, we were looking at reconfigurable architectures on multi-cores where you could sort of morph the hardware to meet the needs of the software, because no concurrent program sort of behaves the same way throughout its execution. It goes through phases. And we could do some of it by playing around with sharing on the caches, and you could go the whole gamut from CMP to SMP. And in that context, it's really important to have your concurrent programs not have race conditions. Any comments on this?
So I'm not entirely sure what the question is. What I got from
what are the
comments,
kinds of abstractions one should be looking at?
I'm afraid I'm going to have to say it depends. So first of all, my specialty is only weak memory models. I'm certainly not an expert in any other bits of the ARM architecture. Yeah. For concurrency, it seems that the sort of abstractions we've got in the CAT models, in axiomatic models, is well suited to communicate the envelope of behaviors rather than constraining the description too much, so that we corner ourselves out of certain behaviors that should be allowable. So that's the abstraction we've been going for in this specific case. For the rest, I'm not sure I know.
Are they good for hierarchical cache models, or for things like persistent or non-volatile memory?
So far, this seems to be, yeah.
Yeah, okay, great.
Rena, if you would like to ask your question.
Hi, Jad.
Hi.
You can probably guess why I'm asking this question. Jad used to be a colleague of mine when I worked at ARM. Does the formalized nature of the memory model give any advantages or present any challenges when you're verifying or validating the in English architecture specification? So when you have, you have some tech authors, which I used to be one, writing all this in, say, the ARM, like, does the fact that you've created these formal models make it any easier to kind of verify that work compared to sort of what the sort of pipeline to the specification might have looked like in the past?
So I think the answer is yes, but only because there's still a lot of human work going into checking that the English rendition and the formal model correspond. So then if we make sure that this correspondence is there and has not been sort of tempered by typos or misguided rewritings, then yes, that's the case. But that's only to an extent. Again, there's a lot of human effort between that's in the interaction between myself and one of our tech author colleagues to make sure that we're still sticking to that one-on-one correspondence. Then we land on our feet because the model can be debugged, the executable model can be debugged. But the weakness is in the making sure the correspondence is there.
Cool. Thank you.
Yeah.
Paul?
Hi, yes, so how difficult would it be to formally verify that the implementation of the ARM processor, or one of them, actually satisfies this weak memory model that you work on?
Did you say how difficult?
Yes, I mean, is it feasible at all? Would it be feasible in a few years?
I don't know. So I suppose you mean only the the behaviors of the implementation that pertain to concurrency, and for example, doing some sort of a correspondence proof between an RTL description and that model. Is that what you mean?
Uh-huh.
Yeah. So I'm not entirely sure how you would extract from the RTL exclusively the concurrency concerns, but if you knew how to do that, then I think essentially you'd have to tackle a correspondence proof between the axiomatic model, this memory model, and the sort of operational model. That's the RTL design, but with all the uninteresting bits erased.
Okay.
That sounds like not entirely infeasible, but a lot of work.
Is it something anybody's contemplating?
Sorry, at the moment at ARM, you mean?
At ARM or anywhere? I mean, is it still a huge amount of work?
I think it's a huge amount of work. Yeah, like I said, the bit, I'm not even sure where to start erasing in the RTL what's irrelevant to the concurrency aspects. And that would be my starting point.
Uh-huh. All right, thank you.
Thank you very much, Jot.
Thank you.
Annabelle, if you're here.
Yes, thank you. I am. Can you hear me?
Yes, I can hear you.
Okay.
I cannot see you though.
Do you want to see me?
Sure, why not?
Here I am.
Great.
Okay.
Do you want to share the slides?
Yes, I shall share my slides. There we go. How is that?
Great.
Okay.
So our next speaker is Annabelle McIver. She is a professor at Macquarie University. Her research in general uses math to analyze security flaws in computer systems. And today we are going to hear about how to change the mind of a government.
Well, thank you very much. Yes. Thank you very much, and thank you, of course, for inviting me to talk today. So this work is obviously on the theme of from theory to practice, and it's mostly going to be reporting some work by a master's student called Gabriel Nunes, who's from UFMG in Brazil, and he's jointly supervised by myself and Mario Alvim. So Gabriel's topic was to provide a comprehensive and rigorous analysis of privacy vulnerabilities of some very large data sets. So where the rigor comes from and sort of what's sort of relevant for formalizing things is that we used what's called quantitative information flow, which I'll talk about in a while, to provide the formality that we needed to produce this study of the security vulnerabilities. And I'll just say that for me, it was a very pleasurable surprise that the quite abstract ideas that I've been working on for many years, for over 10 years, and that I spend time writing papers on and trying to get them published, it was very pleasurable to see that actually a lot of that has had and is having an impact on an actual real life scenario. So let me just tell you a little bit about the background of the problem. So governments obviously collect huge amounts of data about their citizens, and then they use that data to formulate policy, obviously, but they also share it. And in Brazil, in particular, for the data sets I'm talking about, there has been a long history and tradition of sharing some of these data sets. However, as we all know, there have been some rather unpleasant stories. There have been some rather unpleasant incidents about people being damaged by privacy breaches. And so governments around the world, Brazil included, have been enacting laws to protect the citizens, not only between the way that governments can publish and share data to sort of anyone, but also between governments, between government agencies as well. So, so the data sets in this talk are looked after by this organization called INEP. It's got some Portuguese name, which I won't dare to pronounce, but it's about, it's about, it's data collected, which records things to do with children and adults being educated. So it's a educational census. And it's been published in microdata, which I'll come to in a moment, from 2007 all the way to 2020. And it contains information about kids at primary school, at high school, in tertiary education, on teachers and professors and adult education, all of that kind of thing. So it's a very rich data set and contains all kinds of things about these people. And it's millions of people as well over those years. So what is microdata? So this is just made up for this talk. So what we have here is it's being de-identified. So each of these rows in the data set corresponds to a person, but the person's name, so the obviously identifying information, has been removed, but then it's left in this example with age, gender, occupation and illness, you know, things like that. So obviously some of the information collected can be of a sensitive nature. Now the problem with, well, so why do you want to publish microdata? It's because it's all of the data, and so it's you can do all kinds of statistical analyses on these kinds of things, and for transparency as well. But the problem that was noted, you know, in the US Census, you know, over 20 years ago, is that if you publish, even if you take away the name of the people, what's remaining in the profile is actually something which is highly identifiable. It's kind of like a unique profile of these individual people, which then can be put those people at risk of being identified in other ways, so that they're actually then named in other ways by combining it with other sorts of data sets. So this is the problem. So for example, in this data set, not only can you identify people, which is one of the problems, you can also infer some information. So for example, in this particular data set, as we'll see in a moment, if you're female and your occupation is 3, you can actually figure out that people with that profile are 6. So there's these, in this particular data set, so there are attacks, which we'll see, which not only identify people, but also allow sensitive information to be inferred about groups of people, and so it puts those groups in a position of vulnerability. So just a tiny little bit about this new privacy law. It was passed in Brazil. It was passed in 2018, and it comes into force in 2021. And so the particular part of the law is I'll tell you about is Article 12 about anonymized data. And the basic thing is that it's fine. Yes, you have to anonymize the data somehow so that individuals cannot be re-identified. But the anonymization is described in the law as being something like, well, you can't just remove the names of people. You've actually got to make sure that if it turns out that the way that you publish the data, individuals can be re-identified with not too much effort, then that way of publishing is regarded as not anonymized, and therefore, I guess, potentially in violation of the law. So this was the sort of one of the impetus for the guys at INEP to try to seek some help. So first of all, to find out how vulnerable is their data to publication and sharing in the way that they've been sharing them. And once that has been established, moving forward, how do you figure out the best way to publish the data so that it complies with the law, so that it protects the citizens, but yet the same thing is as transparent as possible, because apparently, according to my colleagues in Brazil, the real one of the issues in this scenario is that they have had this very long tradition of publishing this, being very transparent, publishing this data, and so there will be some kind of pushback to change those traditions. So just as we've heard in the last talk about how to go from you know, some kind of formal methods and using them in practice, the same, when I was listening to that, I was thinking, well, the same thing was actually happening here. So obviously they're in Brazil, I'm here, so I couldn't be involved in those meetings, but I will report, they reported to me the what they had to go through to convince the people at INEP, who were actually very eager to have help, but the help that they needed, the help, as academics had to be done was to explain the help that could be done in a way that the people could understand that it applied actually to their situation. So, so the next few slides is just my summary of what happened over many meetings in order to convince the people at INEP who wanted some help, that the problem was maybe a bit harder, and they needed to look at some of the ideas that we were offering in our sort of academic work. So here on the left-hand side is a representative of the academic, so he's a mathematician, and on the right-hand side is perhaps somebody who wants help but is a little bit skeptical about the sort of help that might be available. So, so the first sort of meeting was that, yeah, we have a privacy problem with our data, and then maybe the mathematician will say, yes, okay, tell me about it. We've done lots of interesting research which might help. But they say, it's got to be quick, you know, we can't spend years and years, you know, researching on things. So we need a solution very quickly. You respond saying, but look, this is quite a hard problem, and it's not actually clear that anyone knows how to solve it. And what comes back is this sort of like a little bit skeptical that, you know, these deep academic theories could solve things. And they say things like, well, we know about the birthday paradox, but that's sort of not the real thing. And don't you understand that these problems are real? These are about real data sets, you know. And then the next response is, well, so what you have to do is you actually have to convince them that the problems that that we as academics can look at are actually applied to their own situation. So you have to spend time convincing, time had to be spent convincing them that the problems could actually be addressed by some of the techniques that we had. So the first thing was, well, I've looked in your data set and actually I can re-identify myself. And that was still not good enough. They said, yes, there's always going to be one or two outliers, but surely, and then you have to say, well, actually, the problem is not just about me, it's actually about you as well, because we can find people, you know, in there that that would be a concern to you. And the response is, oh, how on earth did you do that? But surely that must be a fluke, you know, still. So there was a little bit of pushback. And finally, you say it's actually widespread, because 80% of the students, using just our preliminary look at what's going on, we can actually re-identify many, many students in your data set. And at that point, of course, you say, well, the technique I was thinking about was something called K-anonymity. Maybe that doesn't work then. And then so the conversation was, look, we do have some of these new techniques. We think we can apply them to your data, and we think we will be able to give you the analysis that you need to go back to the government and tell you that although these data sets are being published although there is this tradition, things have to change to comply with the law. So, so that was kind of like the time had to be spent going from theory to practice, just convincing the people that the techniques that we had were applicable and were giving them interesting insights into their own specific problem, and it was really their problem, and it worked for their particular scenario. So then they could go on to the next stage, and we could actually start looking at their data and looking at the vulnerabilities inside of the data. Now, as I mentioned, the problem of microdata has been known about for a very long time, and so there's been a lot of work on the literature in the intervening time, looking at large data sets and trying to understand different types of attacks and different types of vulnerabilities. So one of the things, and there are many of these things. So one of the things that was important to do for this is obviously to advise the government the scale of the attacks investigated had to be as broad as possible. But these were written by lots of different people, lots of different times, over lots of different data sets. So what we needed was a sort of like a unifying principle, a unifying model, where we're able to look at the relevant, select the relevant attacks, and express them in the same sort of way, in a way that could be explained to the people, to the inept people who were looking after this data. And the big sort of, the research aspect to this was that these things had to be conducted at scale, because these data sets are very large indeed. And although I mentioned at the beginning, we've been looking at these kinds of things over many years, we haven't ever done any of this at scale. So that was a very important aspect of this whole study. So, so let me just, obviously I don't have time to go over the whole categorization of the vulnerabilities that we looked at, but here's just a couple of them. So we looked at re-identification attacks, where the adversary's goal, you want to find a specific person in the database, or as many specific people in the database as possible, and also attributed inference attacks. So that was, as I mentioned earlier, that is where you can make from some data, you can infer some property about some small group of individuals, and thus putting them sort of at risk. Other interesting things about this problem is that it could be single database, but as I mentioned before, these databases have been, this data has been published since 2007. So there's this longitudinal aspect to the data where you can sort of clip together data over years and learn even more about the individuals inside of the data. So we had to look at that aspect too. So the technique that we used was quantitative information flow, and here it is on a single slide. It's basically a mathematical model which allows the amount of information leaked in some data sharing mechanism, which is what's happening here. So it has a notion of a secret, so what you want to keep secret. It has a notion of how that information either completely or partially might be published, and it allows the assessment of Bayesian adversary. So in other words, a Bayesian adversary taking together the information sharing mechanism together with possibly prior information and putting it together with auxiliary information to figure out whether the adversary can actually find anything out about the sensitive, the secret information, the sensitive stuff. So there's also a notion of leakage, which provides a nice way to provide an explainable measurement of how an adversary can actually use that information for their own purposes. And as I say, we'd never done this at scale, so this was the big thing for us. So, so here's just a little schematic about what's going on. So there's, so these aspects are all what we can do with a quantitative information flow model, QIF model. So there's the prior knowledge, there's the auxiliary information, there's information about how the data is leaked or shared, and that's all put together using sort of a Bayesian analysis to infer whether the information leaking mechanism provides enough stuff for the adversary to use. How might this work in a real situation? So here we have a database, and you might just know some sort of basic statistical things about who is in the database, but you don't know individual people. Here you might have some auxiliary information which you can get your hands on to put together with some information that is shared from the database, and that can all be put together to potentially identify some famous or not so famous individual inside of the database. And so what we wanted to do is provide a measure to see how likely or how possible that was for somebody to do. So the QUIF model, the mathematical model, we can randomly sampling over a database defines the prior. We assume that the adversary knows the information sharing mechanism, and we can express how difficult it is for the adversary to get a hold of auxiliary information and the intent of the adversary inside this thing called a gain function, which is kind of like a generalized entropy function, which describes how vulnerable secrets are within particular scenarios. And then what you can do is you can examine the posterior results and apply the measure to see the difference between what can be done without all of this stuff and what can be done with all of this stuff. And you can compare the difference. So how does it work on this little example? So we start with a particular data set. We can generate the prior by randomly sampling, and it also defines the information sharing mechanism, for instance, by choosing particular columns to publish and maybe suppressing other columns. So how would it work here? Suppose we were trying to keep secret whether somebody was sick or not. So random sampling says in that particular data set that 50% of the people are sick and 50% are not sick. You might just want to publish occupation, which is the column here. So this describes the information sharing channel in that particular scenario. And here we have the relationship between whether you're sick and your occupation also derived from the data set. And so when you put all of that together, it turns out for this particular data set that if you have occupation 3, then you are sick. But if you have occupation 4 or 5, then you are not sick. So that you are actually able to infer, if you had sort of extra auxiliary information, that that you've accidentally published, that if you're in a particular occupation, then you're sick. And then if you know that somebody is in that occupation, then you know this thing that they might not want you to know. So how many vulnerabilities?
Sorry to interrupt. If you want to leave time for questions, you have to wrap up in 3 minutes. In 3 minutes,
I'm going to wrap up in 3 minutes. Thank you. Yeah, so this is just one of the many graphs that were produced here. This is sort of like a heat map. So on the bottom is the number of potential columns which you could be published in some combination of a particular data set. And on the vertical axis is the number of individuals identified. And you can see that around about 5, there's combinations of 5 columns where more than 40% of the individuals are identified. And so this allowed, this has now given the INEP people the evidence that they need to go back to the government to say that they must change what they're doing. So just to summarize what we did, what the theory did to help with this practical situation, it provided a uniform framework for modeling inference attacks from the literature. It also enabled it also enabled the degradation of privacy and the exposing of vulnerabilities to be sort of explained to the people, to the INET people, and well, so also for the theory side of things, we really needed to be able to do this at scale, but being able to formalize these things, we were able to come up with algorithms to calculate these numbers. And so thank you, that was all I wanted to say.
Thank you very much. Sanjiva has a question, and everyone else, please type the questions or get in line. Go ahead, Sanjiva.
Annabelle, that was a fascinating talk, and I loved the idea of the quantitative information flow and the Bayesian adversary. It's really very intriguing, and I like the idea that you could give feedback to the government about their privacy or confidentiality problems. I was sort of intrigued with the idea that since integrity is the dual of confidentiality and information flow models, did you consider seeing how untrustworthy information can flow to the government and thereby vitiate their decision-making capacity by disinformation? Just turn the people upside down.
Yeah. We haven't done that, but obviously it is clearly a big thing, and that would be a really interesting thing to look at. But I have to say, I haven't done that. So we were just looking at, it was more like publishing, because I think a lot of these data sets are just generally available to whoever wants them. I believe that they're not available now, but so we were really looking at the other way. But obviously, one aspect is if you are not careful with the way you share, then the information that you put out could be not very accurate, which is a form of disinformation, right? So it's got to be done very carefully. But this first stage of the analysis was just to look at vulnerabilities and to explain them to the INET people. Yeah.
Thank you. Madhu, go ahead.
Yeah, so I was wondering how differential privacy fits in here, in the sense that, you know, unless you do differential privacy, there is really no guarantee that you won't be de-identified. So is that not a public policy that can be accepted, or is that, is it too much loss of information?
So what I should have said, that this is like the first part of a longer term goal of using techniques like differential privacy. And so I think what we've got at the moment is we've got a nice benchmark for, these are the vulnerabilities. So the next stage would be to select, well, how are we going to publish it? And definitely one of the things that we will need to do is to look at using differential privacy on these data sets. But I kind of think the nice thing about it will be, well, let's use some differential privacy. And I mean, there's how precisely do you use it, and how do you do the settings for it? But now we've got these nice benchmarks, so we can actually compare, and hopefully that will advise the INET people how to do the settings to get the privacy that they want.
Okay, thank you.
Shankar?
Sure. So, Annabelle, you know, this idea of inferring from an attribute, you know, one attribute, whether the person is sick or not, might be a legitimate use of the data. I mean, somebody might want to analyze that. So how do you make the difference between something that is potentially privacy threatening and something that is actually valid use of the data?
Yeah, whenever I think of this, I think, yeah, I don't know, because obviously that's why you collect the data, right? Because so that you can make these inferences. So I assume that what they're worried about is that they don't mind the government making the inferences, but they do like, you know, Joe Bloggs down the road making the inferences. And I agree with you. I do not know how you choose what is legitimate and what is not legitimate. I guess this is one of the things that makes publishing so tricky. And it might be, I don't know, we'll have to wait and see what they say. It might be, they say, you know, these things are okay, but maybe it's just going to be re-identification that they care about. But I think in the remit of the looking at the vulnerabilities, the inference attacks had to be considered as well. But I agree with you, I don't know. So, and you want the inferences, that's why you have the data. But yeah, but it'll be interesting to see going forward, yeah, what will be decided.
Phil?
That was an amazing talk. Thank you very much. My intuition here is still really poor. So I was wondering if you could give a concrete example of some actual database you looked at and an actual leak that happened that you wouldn't want to happen.
Well, so from memory, there was in this data, in the data sets of these INET data sets, I think there were, some of the information collected was whether or not people had disabilities. I think that was one of the things. And for various reasons, they didn't want whether particular people had these disabilities. And it turned out, I can't remember which, there were certain columns, but unfortunately I can't remember the precise columns it was, but they were very, very correlated. Maybe it was the way you traveled to school or something like that, and which town you were in, or if it was
being
the
a politician with being able to apply logic.
Pardon?
Or being a politician with being able to apply logic.
Does that exist? I don't know. But yes, but that was one of the things that did come out. And I'm sorry, I can't be more precise on this. There were so many. Gabriel did such a lot of work on this. There were so many. But the one about the disabilities, I think, and you know, there were other. It's kind of, you look at these data sets and you think, why are you collecting that? And it turns out, you know, because it just seems wrong, some of the data that's being collected. But it's collected for presumably legitimate reasons, and you really don't want those kinds of things, because I mean, to me, it seems unpleasant why they would collect certain types of data. But yeah, sorry, so I can't. The only one I can think of is about the disability. So sorry about that.
Helps a bit. Thank you.
Yeah.
Okay, since we have run out of time, I'm going to. There is one more question, but I'm going to officially call the end of the meeting and stop the recording. But after this, Supratik, you can definitely ask your question and Annabelle can answer it, I'm sure. Thank you to all the speakers today, and we will see you tomorrow for the last day.